So, uh, so today we will get all you wanted to know about image sensors and more from Roger Smith, who is variously a detector engineer, detector physicist, and in short, a detector guru who's been played a major role in detectors at Caltech for the last 20 years or so now. And most recently, Roger was the lead for the ZTF 16 Mosaic camera, which is not the largest, but it's the most highest density. If you take the sensor area and divide by the volume of the cryostat, I think we beat the next one, LSST, by some factors of 5, if I'm not mistaken, maybe even 10. Anyway, Roger's worked not just on CCDs, but also on infrared detectors, and now moving into CMOS, and working on the UVEX detectors and more. Okay, Roger, all yours.
Okay, thanks for the introduction. I'd like to say, oh, by the way, Jan, are you going to record this? You might want to start now.
It's already on.
Oh, good. Excellent. I want to say that everything I do is backed up by a team of several detector engineers. I don't do this all by myself. However, it's been my passion to work on this for my entire career. So, in fact, you'll see that this talk actually spans much of my career. And in fact, what I'm going to do today is to focus most on 2 detector technologies, which are microchannel plate image intensifiers, photon counting systems, and then work our way across to CMOS image sensors, which I believe are the most relevant to ultraviolet astronomy, essentially because they're radiation hard and UV astronomy is necessarily done in space. We'll stop along that journey. We'll stop and look at CCDs more because the thing that makes a CMOS sensor good is the extent to which it emulates a CCD. And so understanding how a CCD works is a good springboard to understand CMOS sensors. So let's see if I can get this to advance. You don't need to see an outline yet. But here is a list of some of the things that you might put on your wish list. On the left, we've got things we want more of, and on the right, things we want less of. And in bold, I've highlighted the essential tension in detector world. The image sensors traditionally, which have given us the lowest read noise and the lowest dark current, have been photon counting systems which employ avalanche gain. The unfortunate thing is that the photocathodes that are required for these sensors don't deliver particularly good quantum efficiency. And so one is torn because you actually want high sensitivity and you want low read noise. You want to have it all. Now, in the course of my career, the situation has improved considerably so that the trade-off is less severe, which means that it's less clear which one to use. And so we'll take a look at this in quite some detail. So the low read noise drives us to intensified systems and did so even before CCDs arrived on the scene. And the high QE, I'm just getting my mouse in the right place, moves us to integrating sensors, which are photoconductors. The reason the photoconductor has high QE is essentially because every photon that makes it into the material to get absorbed promotes an electron from the valence band to the conduction band. So the internal quantum efficiency of a photoconductor is essentially 100%, and the problem then reduces to making an AR coating. So let's think about noise, because this is what drove the world to use avalanche gain. So I've drawn in here a noise distribution, just a normal distribution for read noise, and then offset that by 1 electron. And you can see, of course, that the two distributions overlap, and therefore we don't know whether we've got 1 or 0 electrons, or not particularly well. So we invoke some mechanism to apply some gain to the signal, and we attempt to pull the signal away from the noise to increase its amplitude. Now, it would be nice if the histograms actually look like this. You'll see in a moment that they don't. But the first thing I draw your attention to is the fact that when we apply gain, there are statistics in the gain. The gain varies from event to event. So in fact, there's immediately a penalty for an avalanche gain, and that is the noise in the gain. So your shot noise is increased from this gain variation, unless you do something about it, which we will in a moment. We would be much worse off if we applied the gain and had worse than shot noise. But what we can do is put a threshold into the process so that we don't care how much gain we have. We just know that we have enough, and we discriminate the signal from the noise. And isn't that wonderful? Well, we're not quite there yet. We likely will have more than 1 electron in our signal. And so we would in fact like to count how many there are in any given frame. And so we have another requirement that the histograms not overlap with one another when we have multiple events. And that requirement is essentially saying that we have, if the noise has a sigma, we need 6 sigma of separation between the peaks of the distributions for the gain. Now, in the real world, things usually saturate. And so the second histogram might look like this, and it probably overlaps with the first. And in general, we cannot distinguish multiple events from each other. We have another problem that when we set the threshold, there's some overlap between the pulse height distribution from our avalanche gain and the noise distribution. And you can see in orange here, we have some events that are not detected because they fall below the threshold. There's not enough gain. And then even worse, we have noise generating spurious counts, which show up as dark current. So that's a bad thing. So we have to shift the threshold across to avoid the dark current. And in so doing, we lose more events below the detection threshold. So next, we have to jack up the gain in order to reduce the number of events that are lost. And so this drives us to avalanche gains in photomultiplier tubes that might have tens of thousands of volts across them in order to get enough gain. Now, more recently, EM CCDs, that's electron multiplying CCDs, have shown up, and these work with very low gain per stage, typically about 2%, but they may have 500 or 1,000 stages of gain. And the result is this exponential pulse height distribution, whose most probable value is unity. So you still have a problem that you have to run them at quite high gain in order to avoid the counting losses. One way you can address this is to read more slowly and reduce the read noise. And so you can move your threshold down if you do that, but this comes at the penalty of a lower frame rate and a larger chance of coincidence losses. Now, if you're confused by now, you could be forgiven. The point that I want to make is that there's no free lunch here. This is not easy. There are a lot of trades to be made in all of these systems. And frankly, you might be wanting a better way. So let's walk through the history of how we found a better way, but I want to go back and start with the early days. Albert Einstein got the Nobel Prize for explaining the photoelectric effect, and the most important part of that was probably that he identified photons as being quantized in the process. But putting that aside, let's zoom in on this red photocathode here and see what happens. We have a photon coming in, and it ejects. If it has sufficient energy, it ejects an electron from the metal. Unfortunately, the electron can travel in any direction. Half of them go the wrong way, so they're lost. So we can't get over 50% QE, and a significant fraction of them don't make it out of the material to the other side where they get accelerated. But those that do can be accelerated by an electric field to hit another electrode, and through a cascading series of electrodes produce quite high gain. Now that's a photomultiplier tube, and it has no spatial resolution. But there is a 2D version of this, which was very popular in the 70s and 80s. And this article here I find interesting because it makes reference to a 2D image photon counting system coming to Palomar in 1973 and being used on the Oak Gun Cassegrain spectrograph. And it just happens that one of my jobs right now is to lead an effort to build a replacement of that spectrograph just 48 years later. However, my first brush with this particular paper came 7 years later in the control room of the Anglo-Australian Observatory on the commissioning run. And this is the author of that paper, Alex Boxenberg. And in the back is me at the age of 25 with the new job of being the support engineer to run this system. And so I got to learn a few things about photon counting in a big hurry. This is a schematic of that photon counting system with the 4 stages. There were 10 kilovolts per stage, so a total of 40,000 volts, 7 amps running through a solenoid wrapped around the outside, a re-imaging lens that relayed the phosphor image onto a TV tube. Now you'll find that this hasn't actually, the scheme hasn't changed very much over the years. It's just become more compact. A significant problem with this setup is that the pixel positions are all defined by magnetic and electric fields and timing. There are no pixels anywhere. It's all done by quantizing space and time on waveforms. And the problem with that is that the pixels can float about. It would take us 2.5 hours to acquire a 10,000 electron flat field with 1% shot noise. And in that 2.5 hours, the pixels would move around. So essentially you could not flat field the device. It was very difficult to calibrate. It had a count rate limit of 1 photon per second. Now, the image intensifier tube is being held by Alex Boxenberg in a later photograph here. There were only 3 of them on the planet. And that's another important thing to learn about them. They were not only difficult to make and expensive, but also fragile. And the project scientist for this instrument was using it on the AAO, on the AAT one night, and he opened up the shutter with the flat field lamp set to too bright and burned a hole in the image intensifier. So there were then only 2 of them working in the world. And I was sent across to the UK to pick up the this particular tube. Let's have a look at how it works. It's kind of a nifty trick, even though we won't be using it anymore after this. An electron which comes out of the photocathode has some transverse velocity, and the electric field which is accelerating it axially is determining the flight time to the next electrode. And the magnetic field can be tuned in relation to the electric field so that the electron does an integer number of complete circles before it hits the next electrode. And this has the nice feature that no matter what velocity or what direction, all of the electrons return to a point which is axially located on the point of origin. And so this actually is a magnetically focused image intensifier. I thought it was really cute. Now, one of the things I had to do with this after we repaired it was to take the camera apart and separate the relay lens and TV camera from the image intensifier, put the glass tube down the middle and refocus it. And with 40,000 volts in a cable right next to my ear, an inch from my ear, I can tell you I was nervous. I had seen lightning bolts in the potential divider as we had breakdown events while we were testing this. And so it was something that I wanted to do quickly. So it's a significant improvement that the modern microchannel plate array, which replaces this, runs at a significantly lower voltage. You can see that there are these small pores which are lined with a resistive material. You have a high voltage across. You have the same arrangement of photocathodes scattering a single electron, which then is accelerated into the surface. You get a cascade of electrons, which are further accelerated by the electric field until you get a splash of electrons hitting the phosphor, a flash of light. It's relayed onto a fast image sensor. The image is processed by a computer that sees a flash at a particular pixel and counts one photon. And of course, you have to do this fast enough that you do not get more than one photon on any given pixel. So you have a significant dynamic range problem. Okay, here's a picture of the Galax microchannel plate array. Galax had a failure while it was in flight, so I would like to suggest that perhaps these devices are not quite as reliable as we would like, but they have one very, very important feature, which is that they have a steep roll-off in their quantum efficiency, which renders them solar blind. Shule Nixad will be giving a talk in a few weeks' time and will focus on the quantum efficiency of silicon detectors and the coatings that are required in order to achieve a comparable solar blindness so that our dark current is not overwhelmed by the red leak in our filters. All right, so in summary, avalanche gain is noisy. We can miss events, we can have coincidence losses, we can have spurious events due to sensor noise. The photocathodes have low QE compared to much lower QE compared to silicon sensors, maybe a factor of 5. It's difficult and expensive to implement very large focal plane arrays. You can burn them up, they wear out. You can suffer from voltage breakdown. And one last point I'd like to bring to your attention is, yes, they can kill you. So a significant improvement in the going to semiconductor sensors is that I can kill the sensor, but they can't kill me. All right, so let's talk about silicon. All of that was just preamble, and I'd now like to review silicon sensors in general without really differentiating whether we're talking about CCDs or CMOS. We'll see the differences between CCDs and CMOS in a while. I'm going to ignore some other classes of avalanche, photodiodes, and so forth, because they essentially suffer from the same drawbacks as the microchannel plate array. So the big deal with the silicon sensor is, as I mentioned earlier, that the QE is basically 1 minus reflectivity. So if you can do really good coatings, you can get really good quantum efficiency. The proviso here is that the CCD has to be thicker than the absorption length of a photon. Now, the absorption length in the ultraviolet is extremely short, so that's in fact a very easy requirement to satisfy, less so at the red end of the optical bands, but we're not worried about that today. So here is the absorption length curve across a very wide wavelength range. And so you can see your silicon detector actually can be used all the way from X-rays through to the near infrared. And we're interested in this little slither down here at 100 to 300 nanometers, where the absorption length is at a minimum. This diagram just illuminates the relative thickness of various layers in silicon sensors with a focus on CCDs. And what you can see here is that when we're down at the ultraviolet end of the curve here on the left, that the absorption length is in fact shorter than the thickness of any of the electrode structures which we might put on the front surface. And this means that we absolutely have to illuminate the sensor through the backside so that we don't lose our electrons in the electronics. So this view here shows you the silicon from edge on. So we've got the back surface on the right, and the electrodes or circuitry are on the left here. It's bonded usually with epoxy onto some usually metallic package, or it might be silicon carbide. But we've got some layer of silicon. In CCDs, they might be as much as 250 microns thick. For an ultraviolet sensor, you might be down to only 5 microns. So a photon that makes it through the AR coating generates an electron hole pair close to the back surface. And in that area, there's no electric field. And so the electron and hole just wander around by Brownian motion. And they may actually go in the wrong direction and get reflected off one of the edges. So it's very important that they not get stuck there. Shule is going to talk about some problems with that and the solution to those problems. But let's assume that the electrons eventually bounce around and then they move into this area to the left where there's an electric field. We'll come to why there's an electric field there in a moment, but the electric field sucks the charge across towards the other side where it is isolated from the electrical circuits on the surface by an oxide layer, an insulator. And basically it's charge that's trapped, attracted by a capacitor plate. All right, so the backside, the AR coating problem is fairly significant because these plots show you silicon in black and various other materials going through quite violent changes in refractive index in the range of wavelengths that we're interested in. And so Shule's group work extensively on developing coatings that can cope with this. I'm not going to get into it myself. I'd rather stick to the schematic part of the detector layout. This shows what happens when you put long photons in and they pass all the way through the device and they bounce backwards and forwards in the silicon, and some of them go into the epoxy layer, and you get an etalon effect, variously known as etaloning or fringing. We don't have to worry about that either because our photons get absorbed so close to the back surface that they don't make it all the way through. So when the wavelength is very short, we can run into a second effect, which is that the charge can wander transversely before it finds its way into the electric field and the pixel. And so we would like to minimize that. And another thing that happens is that if we have enough energy, we can in fact generate more than one electron per photon. And it requires a bit of thinking to decide whether or not this is a bad thing or a good thing. It's actually a good thing if your read noise is limited and you'd like to boost the signal above the read noise or the dark current. And it's a bad thing if your shot noise is limited because this process is in fact a noisy process, just like avalanche gain. And so you actually introduce some excess noise to the signal. It actually is only a significant problem towards the shortest ends of our ultraviolet wavelength range. But for the far UV, it's something that we definitely need to calibrate and understand. So it complicates our exposure time calculators. Right, so homing in a little bit more on now a UV version of the sensor, the first thing we want to realize is that we want it to be thin. And these curves on the right show the interaction of the absorption length with the wavelength and how that affects the quantum efficiency. These are quantum efficiency curves, I think, for an uncoated device. And they show that we really would like it to be as thin as possible in order to kill off those red wavelengths, which are in the solar spectrum, which we would otherwise need to be rejecting with filters. We still need the filters, but making the detector thinner does help. And you can see here as well that as we make the device thinner, we're also making that field-free region thinner. And this helps us with the lateral charge diffusion. And a third benefit of a thin device is that cosmic rays tend to produce short tracks that traverse only 1 or 2 pixels because the pixel is now thinner than its width, it's shallower than its width. And so the aspect ratio is favorable. All right, now let's start to build this sensor up. The charge.
So Roger, why
Yes.
not make it ultra thin? They still, why is there, what sets the What's that?
Yeah, actually, I'm quite happy to have questions while I'm talking, by the way. The reason is that it's not impossible, but it creates a surface passivation issue, Sri, because when we have an electric field at the back surface, we tend to increase the dark current. And so we have to passivate the surface very well. But with Chalet's delta doping method, I think it's very interesting, and we should be experimenting with a super thin device. So I'll move on, but I'll hold that thought. That's an important experiment for us to do. Okay, so one way of making a sensor then is a CCD. And so what we do with a CCD is we just put a whole bunch of capacitor plates. Imagine that the capacitor plates are long and thin and going into the page. We'll worry about how we subdivide the pixels in the other direction in a moment. And all the blue ones are going to be connected together, and all the red ones, et cetera, et cetera. What we do is we put a negative voltage on some of those electrodes, one or two, to create a barrier to separate one pixel from another, and the charge stays close to the positively charged capacitor plates. So we can manipulate these voltages to actually move the charge across the device without actually mixing. And I'll show you how that happens in a minute. But before we do that, let's look at the difference between that and a CMOS detector. All we do with the CCD, we turn the CCD to look like this. So that's CMOS, CCD, CMOS. So what we do is we replace one of those electrodes with some circuitry which is able to convert the charge to a voltage right in the pixel and relay that voltage across the device on wires to the edges. And so that's the actual quintessential difference between a CCD and CMOS device. CMOS convert charge to voltage in the pixels. CCD, we move the charge to the corner and then we convert. And we'll get into how to do that in a moment. So you can see here, I've just drawn in some little arrows showing how, in fact, we do not need to lose light where we have that circuitry. What happens is we set up the potential on the charge collecting side, the side the charge is coming from. Above the circuitry, we make a negative potential, and that drives the charge sideways into the pixels. So in fact, we get 100% fill factor on a backside illuminated CMOS device. So people often talk about which is better, CCDs or CMOS? And my answer is, depends on what you're trying to do. If you really want large format and you want the ultimate low dark current, CCDs still rule. If you're in space and you're worried about radiation hardness and you don't want a mechanical shutter, CMOS is extremely attractive. And you'll see as I go forward with this talk that the CMOS is really gaining traction and particularly interesting for applications in space. But we're going to talk about CCDs for a moment. It was invented in 1969, the year that the Beatles released the Abbey Road album, and I was still in school, and they landed on the moon. Just to get context, you'll see Jim Janicek, whose name is at the bottom right-hand corner. His name is written on this CCD. He was a guy who was developing the CCD technologies and basically wrote the Bible on CCDs and taught us all how to use them. He's now actually designing the CMOS device that I'm going to show you data from later. And Dick Bredhauer is the other name on this device, and he eventually founded a CCD design company, which is about an hour and a half down the road from here, called Semiconductor Technology Associates. But this particular picture shows a micrograph of a CCD that went on the Cassini mission, and you can see basically all the pieces of a CCD just by looking at it. If you know what you're looking at, you can see all the electrode structures running left and right, and there are these little ripples that run up and down the page are in fact doped lines which partition the columns from each other. And the way it works is the charge is transferred down the columns by manipulating these electrodes that are all bussed together on the left. until they reach another CCD register, which moves left, right, and moves the charge to the corner. And some magic happens at the corner where the charge gets converted to a voltage. Okay, I know I didn't explain that all in great detail because I'm rushing through CCDs so I can get to CMOS. The little cartoon I'm showing you here is the magic. If you look at this mesmerizing little video for a while, you'll realize always one of the electrodes is high and it's acting as a barrier that stops the charge from mixing from pixel to pixel. But in the process of, how do I make this go again? Let me see if I can do this again. There we go. In the process of sequencing through these voltages, high and low, you can see that you either have one in the low condition or two in the low condition, which hold the charge, and so the charge moves along sideways. Now, the key here is that if the charge does not mix and there's none lost, the process is entirely noiseless. So we can move the charge from the point where it was detected to an output amplifier in the corner. Going back to my earlier cartoon of the side view of the chip, we can immediately identify a horrendous problem. And in fact, the inventors, Smith and Boyle, understood this from day one. They understood that there are a large number of defects at the oxide to silicon interface, which create intermediate energy levels in the middle of the band gap, and that electrons get stuck in these traps and left behind as you try to transfer them. And the result is a catastrophe for the charge transfer efficiency. This diagram here is showing the shape of the potential well if you just put a capacitor plate on the surface as I'm showing here. So we need a trick. And the trick that won them the Nobel Prize is that they realized that if they put a dopant into the surface so that the entire CCD became one big PN junction, namely one big diode, that what they could do is drive the electrons into the bulk material below the surface where there are very few traps. And so here we can see in the new potential diagram that the charge rolls downhill, down as the top of the page in this case because electrons are negative. You can see that they roll to the bottom of the potential well, which is marked in yellow. And then as the charge fills up, they nearly reach the surface, but before the charge actually comes into contact with the surface, it starts to spill over the barrier potential, which is drawn as this other line here. Now, in the actual CCD, one of these potentials is sort of into the page and the other one's closer to the view. You know, there's the direction of travel of the charge is into the page. And so charge will bleed out of a pixel that overfills before it reaches the surface, so you don't get trapping at the surface. Anyway, this is the trick that makes a CCD work. It works extraordinarily well. This plot by our own Pavan Bilgi shows the total amount of deferred charge after 3,000 transfers. And if you go over to high signal levels, 10 to the 5 electrons, the fraction lost is only 12, 15, and that's a tiny fraction of the total charge. Unfortunately, if you cruise over to 10 electrons over here, you can see now that you're losing 1 out of 10 and you're losing 10% of the charge. Now, this is a bit of a catastrophe for UV astronomers with zero sky, and it's something that we're going to have to deal with. And I'll come back to how to deal with that in a moment. The other thing, though, that's magic about a CCD is that this charge transport allows you to move the charge onto an extremely small capacitor. And so if the capacitor is small, the voltage which is induced per electron is comparatively large, with the result that we're able to boost the signal above the noise of these output transistors. And this is the magic that gives a CCD very low read noise. And the trick, of course, is that we need to optimize the geometry of those transistors as best we can in order to reduce the read noise. And so here we've got a plot of the read noise in electrons, and this is a relatively recent paper on optimizing transistor geometry, and you can see that it is actually possible to get down to 0.8 electrons on highly optimized devices. However, we're going to do better than that. It turns out that that got eclipsed when the same designer who was doing that work managed to perfect an idea that Jim Janicek, who I mentioned earlier, came up with 27 years ago, or 27 years earlier. I think it's now about 33 years ago. And that idea was to overcome the limit in the reduction in noise that comes when you integrate. You can see this curve, we're showing integration time, and the curve flattens, and it reaches a floor due to 1/f noise in the buffer transistor, which is insurmountable, except if you can move the charge noiselessly off the sensing node, re-establish the baseline, remeasure the baseline, and then put it back on again. And so the charge skips on and off the sense node. It's called a skipper CCD. And after many, many cycles, you actually can continue to beat the noise down. So you only have to integrate away the white noise because you're actually subtracting the baseline drift out. And you're subtracting the 1/f noise. And so in the blue dotted line, we've got the magic 6 sigma threshold, or sigma is a sixth of an electron. And here is an actual measured histogram of an image. And it shows that each electron level, whether or not you have 0, 1, 2, or 775, 776, can be discriminated in post-processing. And so when you threshold the data like this, you've turned the 0.15 electron read noise into 0 read noise, but you haven't suffered any coincidence losses. You're not required to read out at a high frame rate. Your CCD can have it can have a well capacity of 350,000 electrons. Another remarkable feat is that if you look up here at the dark current, you'll see that the dark current's actually setting a world record. And but first, let's just note, this is self-calibrating. You can tell the gain because you know how many, you just count the electrons. Just make a histogram of a flat field and you know the gain and the linearity because you just look for the peaks in the histogram. No size or formats limits, no clock-induced charge because you're reading out so slowly. Whole dynamic range doesn't wear out. It's amazing. And to boot, this particular device has actually registered a dark current of 1 electron per pixel per 1,000 days. And there was some skepticism in the field about this. And so the team burrowed down and redid the measurements and wrote a paper dedicated to just this and released the paper a few days ago. And now they've got error bars on the number. So they've actually reduced their estimate of what the record dark current is. Unfortunately, this measurement was made in a device that takes about an hour to read out because of this skipper mode. And one would need to respin the design to have maybe 100 output amplifiers in order to get that readout time down to reasonable numbers. Now, you might be tempted to do that.
So Roger, I have a question. The
Yes.
ultimate read noise,
Yes.
not a dark current read noise, is due to the FET itself.
Yes.
Fine. I'll say in what is the limit to that? I mean, these are all operating at room temperature. Is it a temperature issue? Is it the quality of the FET? What is it?
There is Johnson noise in the channel resistance.
That's
And-
proportional to temperature.
Yeah, if you went cold enough, you could make it
Yeah.
lower.
So yeah, we'll make it cold.
Well, we're already done that.
No, we can make it even more cold. I mean, where's what's the thing?
Well, eventually, I think eventually what happens is you freeze out the carriers in the CCD and it doesn't work as a CCD at the temperature at which the output amplifier becomes usefully quiet.
Okay, but are you saying that the output amplifiers in CCDs are already at cryogenic temperatures?
Yeah, that buffer out amplifiers at the 150 Kelvin that the CCD is at, and the voltages are very small. The other thing, Sri, is that there are trapping processes in the transistor channels which trap and detrap. The other things that create the 1/f noise. The white noise is thermal. Yeah. Okay. However, we've solved it, and it's going to be solved even better by the time I'm finished with you. So let's stay with this. The skipper allows us to beat the 1/f corner, which is caused by the traps in the transistor. We're fundamentally limited by the 1/f corner more than the white noise, and so this technique could be pushed by parallelism. You could make a device that had many of these output amplifiers, but you're still stuck with this problem of charge transport. This image here shows, this is quite a famous paper by Richard Massey, which shows the degradation of the CCD on Hubble and how he developed an algorithm to invert the charge transport problems. Unfortunately, even though it looks very successful, it's not as good as you really want. And we're continually fighting radiation damage in CCDs. And so CMOS is quite attractive because it actually addresses that particular problem. So now I'm going to finally talk about CMOS, which is the thing that I wanted to get to. So where am I at? I'll just check what slide I'm at. Okay, we're good. This little schematic just says, well, what is CMOS itself? It's a process where you can make both P-channel and N-channel transistors on a common substrate. And the trick is to dope a well around the PMOS transistor. If you have a P-type substrate, you put an N well, and there's a PN junction that isolates the transistor from the substrate. And the reason you want to do this is that you want some of your transistors to conduct when you have a high gate voltage, and you want the other ones to conduct when you have a low gate voltage. And commonly this is used for digital logic, where we want to make these push-pull pairs where you can see this input A, when it's high, one of the transistors turns on, and when it's low, the other one turns on, so that the transistors pull the output Q to the low rail or the high rail, but they never conduct through both transistors at the same time. You set up the timing and the threshold so that you end up with extremely low transient current caused by turning both on at once. You want one to turn off just a shade sooner than the other one turns on. So that's all very well, but we actually want analog signal transport on our image sensors. And the particular thing we want to be able to do is, yes, we would like to make P and N type transistors, and we would like to have some logic built into the devices. But what we most want is analog switches. We just want to use the transistors as a switch to conduct or not conduct, or to use it as a buffer MOSFET to operate in the analog regime. And the same transistors will work that way. So, okay, we need to put circuitry in the pixels. And the first attempts at CMOS put the circuitry around the periphery of a charge sensing area, and there was a dead zone as a result. And the first thing people did was they put little lenslet arrays to try and curve the light to land on the active areas and not hit the electronics. This is completely useless in the it's cheap, but it's completely useless in the ultraviolet because the UV photons would be absorbed in the surface. So I just wanted to tell you that there are many kinds of CMOS. It's not one thing. There's so many different designs. So you've got to be a bit careful when people talk about CMOS that you don't lump them all together. The kind we're interested in is backside illuminated. You'll find that every iPhone has a backside illuminated sensor. Samsung phones have them as well. Any good cell phone camera has a backside illuminated sensor in it. And so the way they're made is that the active circuitry is deposited and then it's bonded to a supporting wafer, and the back surface is then ground away, polished and etched until the device becomes very thin, and the electric fields are set up so that the electrons are collected from the entire back surface and they entirely avoid the circuitry that's on the front, so that we don't have any fill factor issues. Now, a CMOS device is very much like a CCD, but it's has half a CCD pixel. It has an imaging area, which you see here, called pinned diode, and that's most of the area of the pixel. And then there's a little skinny electrode that's like one of the electrodes on a CCD, and then there's a sense node. So we do just a single transfer, and the potential diagram that's shown over here at the right indicates that what we do is we reset the sense node to be more positive than the voltage in the light detecting area, so that when we lower the voltage lower the potential on the transfer gate, the charge can just passively cascade down to the lower potential, and then we raise the transfer gate and the charge is now trapped on the sense node. Now the trick here is to invoke another feature of CMOS, which is that because it's been used for digital electronics, the market has driven the lithography for CMOS to the point that we can do very, very fine resolution lithography and make tiny transistors. Tiny transistors have very little capacitance, which means that the CMOS fabrication lines can make devices with very low sense node capacitance and very high gain. A good question, which I'll ask on your behalf, is why not do this in a CCD? And it's a bit complicated in that the answer is to do with the resistivity of the silicon, the purity of the silicon, and the distances that the electric fields propagate through the silicon. CMOS is made on relatively high doping density silicon, low resistivity silicon. And if we built a CCD that way, we would actually have very large amounts of lateral charge diffusion as we make the device thick. So anyway, there are some trades, is all you need to know. The CMOS devices tend to be small pixel devices, which is quite suitable to the small transistor geometry. And it's also quite suitable to making them thin. Now, to get the charge out of the sense node, we just have a bunch of analog switches in a matrix of rows and columns. Every pixel has a switch that connects to a column bus. At the bottom of every column bus is a switch that connects one column and then the next column to a single output amplifier. And so we just raster scan through the device. Now, I've shown this with a serial shift register on the edge here, which implies that you are only doing raster scanning, but we have devices which actually have address decoders so that you can randomly address pixels, which is kind of interesting. So CMOS devices with their small transistors have fast settling, naturally lend themselves to many parallel paths and very high output amplifier count. They can support high frame rates as a result. Another result is that the minimum exposure time can be quite short. The charge transfer process that I just described allows us to actually gate the image without stopping the accumulation of photons, which means we don't require a shutter. It also means that we're collecting photons all the time, so that while we're scanning through all of the pixels to read the voltages, we're still accumulating photons. So we get 100% duty cycle on sky, unlike a CCD, which has to close the shutter, read out, and open the shutter again. So another thing we can do is we can switch in a second capacitor in parallel with the sense node in order to reduce the gain and extend the well capacity of that sensing node. And so we can switch between a low gain mode and a high gain mode. Now, when we're in the high gain mode, we get the lowest read noise. But we can actually do this to every pixel so that we read it first in high gain, switch in the second capacitor, read it again in low gain, and the pixels which are below our high gain well capacity have low read noise, and the pixels that have higher signal, we just choose the high gain setting. So we select between the two readings and pick the one we want. And what this effectively does is it extends our dynamic range up to a well capacity that's more like a CCD. It's about 190,000 electrons on this particular device. Now, because we have 100% duty cycle and fast readout time, we can do another trick, which you also have in your cell phone. It's called HDR mode in your cell phone for high dynamic range. And what you do is you pair a very short exposure with a long exposure. And the short exposure is effectively duplicate imaging time. And so there's a loss of efficiency. So you'd like about 100-to-1 ratio in exposure times so that you're about 99% efficient. And what you do is you pick the value from either the short or the long exposure according to how bright the signal is. This can extend your dynamic range by a factor of 100. And this particular example, which I've drawn here, which shows signal to noise versus signal level, is showing that in fact we have effectively a dynamic range of about 10 to the 7. And so combining the gain switching with this exposure time, dual exposure time, we actually can get a dynamic range which is far greater than a CCD, even as we have 99% observing efficiency. Now, why do we care about that? Well, if we're doing an imaging survey, there's always some number of very, very bright stars in the field, and this allows us to actually capture all of them. And those bright stars actually have some value because they're stars that were observed in the very early UV surveys with lesser instruments. And so it allows us to cross-calibrate a deep survey against a legacy survey. And so I think this is actually kind of interesting. Are these devices available in large format? Yes. Are they available in large pixels? Usually not, but there are scientific CMOS devices like this one shown here, which have decent sized pixels that are reasonably well matched to the kinds of telescopes that we might want to build. So this particular device is under test in my lab at the moment, and I'm going to show you a little data from it. But first, I'd like to comment that one can make large mosaics of these sensors. Remember that CMOS is produced on large production lines. The silicon wafers on which they're made are typically 12-inch wafers, and we can get many, many devices of this size on a single wafer. We produce them in very large numbers so that once you've paid the setup cost, which is quite substantial, the production cost is actually relatively low, which means that building large mosaics is quite feasible. And I remind you of the obvious fact that if you're doing an imaging survey, sensitivity is not the only factor. You want N10-do, you want to have area. It's just as valuable because it means that you don't need as many images to cover a given area. So we get a boost in sensitivity in CMOS, both from the fact that the QE is higher and the fact that we can afford to build very large focal planes quite practically. The gaps that I show here are realistic kinds of gaps for the sort of packaging that we might envisage. This particular image that I'm showing here has an 87% fill factor. And so that's perfectly reasonable. Now, another thing that we can do if we have a wide field sensor is we can use that random addressability of the devices.
Roger, the CCD is the biggest ones are like 91 millimeters.
That's correct.
So what's this is half that? What's the reason?
There's no reason why it can't be bigger. it turns out that big devices have been made, but not in quantity. And Sarnoff, who are producing this device here, would require $300,000 to reprint their mask set to make some small mods to allow us to go up to, say, an 8K squared. And so it's absolutely doable, but somebody's got to fork out the money. There's no technology limit to the size of the device, really, because the yield is so good.
Okay.
Yeah. But anyway, if the gaps are acceptable, using devices that we already have available and just mosaicing them together is quite reasonable, because a 41mm tile is big enough to be practical for making a mosaic. So let's see. Okay. One can use the addressability of these devices to actually read out a subarray without disturbing the remainder of the array. You can be conducting a long science image on the whole focal plane and selectively read some portions at a higher rate. And it would be entirely practical to read out, say, 10 lines at a 10-line high region at 100 hertz. Now, we don't really need that. A few hertz to 10 hertz would be sufficient for a star tracker. But ask yourself, what makes a good star tracker? Well, you would like it to be sensitive. You would like to have a big aperture, but you can't afford to put a second telescope up there with a very large aperture. What you really want to do is look through the aperture of your science telescope and get all of the aperture you have. What else do you want? Well, you want lots of pixels so that you've got good resolution. Well, if you pick your guide stars from a wide field imaging mosaic, that's what you've got. And so lastly, what you want is a fast readout, and you want it to be well registered relative to your science focal plane. So in fact, using subarrays on your science focal plane for pointing control of your spacecraft is actually extremely attractive. Okay, so onwards to some problems. We're not out of the woods entirely. This device that we're testing, Sri hasn't seen this yet. This looks rather horrific, but I'd like to point out that I've got some contours on this. So this is shown in millielectrons per second. So what we're seeing here is a dark current map, but it's not dark current at all. It's photo emission from the electronics. Now, ignore the defect that's on the right-hand side, but what you can see is the 4 output amplifiers that are currently in use acting like lighthouses. We can see the row select logic up the left-hand side, which is also emitting a lot of light. Now, we've been through all this before. Infrared detectors had this problem in abundance when they were first developed, and techniques were developed for shutting down the electronics during the exposure, or for putting a metal mask on the detector in order to trap the light so that it didn't propagate across the detector. And we are in the process of exploring things like that. But how well are we doing? Well, not terribly, but not as well as we want to be. So if I pick that white box up here and plot the dark current versus temperature, I get the red dots here. And you can see that the dark current is coming down. Somewhat perplexingly, it's not following the theoretical curve here in gray. So I would describe a point on the theoretical curve as being somewhat optimistic at this point. But if we were to fit a straight line to the top of the curve and extrapolate downwards, that might be a worst case scenario for what we'll get when we suppress the glow. My expectation is that real life will fall somewhere between the green and the blue. But this is getting us down into the regime where in a half-hour exposure, we might have one dark electron. And so with the read noise that we have at the moment, this would be subdominant. So it's not terrible, but we've got a way to go. So noise. Okay, noise. This is the thing that was driving us partly to away from CMOS and towards avalanche devices and photon counting. So let's see what we can do in CMOS world with the noise. CCDs have neatly dispensed with noise. Can CMOS do the same? Well, okay, this is somewhat intermediate result. You can see this is a map of the noise. Another important point is that with CMOS devices, every pixel has its own gain and offset and personality. And so we have to describe everything with histograms. And so here's a histogram of the noise distribution at different read rates. And a good way to look at this is not to look at the cumulative standard deviation. That's the wrong idea. What you've got to do is add variance, not add standard deviation, because it's noise. And so this is an RMS noise curve, which is essentially a cumulative distribution, except it's been turned around so that it shows the axes have been swapped. So it shows the RMS noise for a given pixel fraction used. So if you use 99% of the pixels, you get 2 electron noise. If you use 100% of the pixels, you get about 2.3. So the noise is not too bad, and there are many, many pixels which are much quieter. So let's think about whether we can make this better. The first thing that CMOS designers had to do is to remember what was learned in CCDs, and that is that we don't want charge traveling along the surface where there are lots of traps. And this is true in the channel of a FET, not just in the channel of a CCD. And so this compares buried channel on the top and surface channel on the bottom, and shows that the noise is dominated by single electron traps, which lead to random telegraph noise. That's square wave appearance, but with random transitions. And that occurs because a single electron in the channel is either trapped or not trapped, and the electric field from that electron modulates the gain of the transistor. So this is the characteristic noise in these transistors that we have to battle. And the other thing that was realized is that holes don't get trapped as often as electrons do, because the process for creating a hole trap is just simply less probable. This is actually important for radiation hardness as well, because PMOS devices are actually more rad hard. So if you want to guess which type of transistor did our manufacturer choose, well, of course, they made the wrong choice, because everybody thinks of collecting electrons, and so they use NMOS transistors when they should have used PMOS. However, the lessons are being learned. A month ago, Hamamatsu published this white paper that I put on the website, which is an extremely well-written document, very easy reading, and I'd encourage any of you to have a look at it. And I pulled out a couple of figures from that white paper. They've shown the evolution of their CMOS devices. On the black curve at the top is surface channel transistors. The green curve is buried channel. The red curve are PMOS transistors with geometry optimization to reduce the capacitance. And what they've done is, as they've reduced the sense node capacitance, they've moved the modal value for the noise to lower values. And as they've put in the buried channel and PMOS transistor, they've gotten rid of the tail. So there's two things they're doing at once. And now, if you look at the histogram of an image, this is following the time history of a single pixel. So frame number is time, and they're just looking at the value of this one pixel and making a histogram. And you can see that the noise is low enough that they actually see a histogram which allows you to actually differentiate between 1 electron, 2 electrons, or 1 photon, 0 photons, 1 photon, etc. So basically, the first CMOS instances of direct quantizing CMOS are now being released. And so we're no longer photon counting in the sense that we have to identify every single photon. We can integrate, and then we can look at the signal and we can identify, we can quantize the signal into the number of electrons, doing the Millikan oil drop experiment just by looking at the data. We can see the quantization of the electric charge, which I think is absolutely stunning. Now, this device, that little black box there is a camera which contains one of these detectors. Apparently, you can order them. Whether they're delivering them, I don't know, but they're publishing a data sheet. You can see it's 4,000 by 2,300 pixels. I want to draw your attention to an amazing thing. That image intensifier that I introduced at the beginning, it had a count rate limit of 1 photon per pixel per second. This one has a 7,000 electron well capacity at 120 hertz frame rate. So it has a 35,000 electrons per pixel per second flux limit. And when you hit the flux limit, it doesn't burn up. Nothing goes wrong. It just saturates. It's absolutely amazing. So with that, I'll take questions.
Okay, thanks, Roger, for the whirlwind tour. Anyway, so I urge everyone to read the Hamamatsu paper, and probably after that you can reread the review Roger's talk. But questions, please. You can just pop in or raise hand.
Everybody's confused.
Okay.
I'm just waiting for someone to ask me, what's the TRL of this new detector? The answer is about 2.
So did you say that the new detector, the pixels were small?
Yeah, they're 4.5 microns, I think. So the device, yes, 4.6 microns. So the device is not that large, right? It's only 10 by 18 millimeters. So this particular device is not quite what we want yet. But it certainly points the way to a fascinating new kind of imaging camera.
Roger, are these devices cheap enough that you can use them on, let's say, CubeSats?
Well, CMOS in general, yes, definitely. The 4K by 2K, which I'm testing at the moment, I don't recall the actual number, but I can remember that we priced it out for a previous mission proposal, and the prices were very reasonable. And so, you know, you may not think they're very reasonable for a CubeSat, but for a small Explorer mission, they were just very comfortable. They weren't terribly expensive.
Thanks.
Yeah.
Roger, this is Todd Jones. Can I ask a question?
Yeah, of course you can, Todd. Hi.
Hi. Well, I was naturally, my ears went up when you're talking about making really thin and thinner and thinnest detectors there. Would you be interested in a situation where you got a smattering of different thicknesses? And so you'd have some which were 0.5 micron, some which were 1 micron, some which were 1.5, just kind of a wedge going across a bunch of different detectors. Because that's probably what you're going to get first off.
You don't mean as a test, you mean that it'd be difficult to control the thickness.
Yeah, right off the bat, it's going to be difficult to control. And so that way you can at least figure out the benefits of different thicknesses.
What I think would be interesting to ask is whether or not there's any etchant which slows down when it gets to the doped silicon, so that can control the thickness some.
Yeah, well, kind of like what we do, but the opposite of what we do with the HNA etch.
Yeah.
It slows down when it hits the no charge carrier situation.
Yeah, well, Chalet is going to talk about red rejection and the extent to which we even need this. I think a mildly thin device, at about the 5 micron level, would be helpful and immediately practical, where we don't thin all the way through the fill-free region at the back, but close.
I see.
That'd be a good start. Another thing to think about or ask about is whether or not they can dope them more heavily so that the depletion region is much thinner. And CMOS tends to have thinner depletion region because of the higher doping levels. CMOS fabrication lines don't like process change. So that's actually a drawback of CMOS. You're kind of dealing with what they give you.
All right.
Other questions?
So Roger, I have a question. What's the wavelength sensitivity of this CMOS? Is it the usual thing, 3,500 to 1 micron, or is it something special?
It's backside illuminated, so it's entirely dependent on the AR coating that you put on it. And so all you got to do is look at the absorption length curves, and you realize that you've got I can't. Oh, there it is. You've got very thin absorption, so it all gets absorbed at the back surface. And so we can work down to 100 nanometers, no problem. The problem is with coating materials to put on the silicon. And in fact, one of the things you can do is you can leave bare silicon uncoated if the coating is doing you harm. And I think that we're considering doing that. Not on the imaging channel, but on the spectrograph. So we have a neat idea for the spectrograph. Chalet I hope is going to present some discussion of tapered coatings, which tune the AR coating to the wavelength which lands on the pixel. So each pixel has an optimized, it's operating at peak QE. And because the coating has a narrowband response, the wedged coating is also rejecting the scattered light in the spectrograph. So it's kind of really interesting way to build a detector for a spectrograph. So you get extremely high QE over very wide wavelength range. I think you'll see more about that in a few weeks' time.
So, Roger, the reduction in the dark current really opens up, especially in the ultraviolet, opens up high resolution spectroscopy, because per pixel, it really matters per pixel what is the dark current. And if your pixel is extremely tiny wavelength, then even one dark electron would be a lot of noise. So yeah, the stuff they had that the preprint you showed about, when then instead of measuring per hour, they're measuring per day. That will make a big difference.
Yes. Now, to get there with CMOS, what we need is we might actually need some design changes that allow us to selectively power and depower different parts of the chip, so that we keep the photodiodes biased, but we don't put power into anything else during the exposure. The other thing, that's not necessarily terribly difficult, but I fear that the device that we're testing here doesn't have that capacity. The other thing we can do is mask off those areas. And I was talking to Chalet today about running some experiments of that nature. Actually painting the chip effectively.
Okay, other questions? Well, it's your last chance. It's the last call, as they say. So, okay, I think not hearing questions, probably a bit late. Some people are signing off. So
I would say, I'd comment that if anybody wants to discuss any of these things further, I'm perfectly happy to continue the discussion later.
Yeah.
Another time.
yeah. Okay, let's sign off then. Thanks, Roger.
All right.
Yeah.
Thanks everybody for staying up.
And good night.
Thanks, Roger.
Bye.
Bye.
Bye.